Today's section you can see, section 2.8, fitting a model to data 2. When we did fitting a model to data 1 in 2.7, we were really taking data points and graphing, see what it looked like. Then we took points and found the constant of the variation. Well, knowing we have the same goal today, I think same goal but different approach. You should hopefully like one or the other. Now, in the reading in 2.8, you read specifically about the converse of the fundamental theorem of variation. We spent plenty of time discussing what happens to y when x is doubled, what happens to y when x is quadrupled. And we kept saying that it was based on the original equation's exponent and that multiplier c. Well, now we are going to be looking at data and looking for those specific relationships. Is the y value doubled? Is the y value quadrupled? That's why we're calling this a converse. So if you understand the forward version, if multiplying every x value of a function by c results in the multiplying the corresponding y value by c to the n, then we should be able to go back and say, then y varies directly. It is a multiplication, and we could tell you exactly directly as what. Is it x to the first or is it x squared? As those are the two we've been working with. And then the same thing applies down in the inverse situation. So knowing how the converse of the fundamental theorem of variation works, we're going to use that same example that was used in the book, the construction guys and their scaffold. So let's start this way. A couple things. They gave you several different data tables, and they always said on the data table that something was being held constant. So I'm looking up here and saying in this one, distance d and thickness t are held constant. Well, remember, your board is three-dimensional. So you have the width of the board, the length of the board, let's call that the width, this the length, and then you also have the thickness, which runs up and down. So there are three variables to this board that we're laying up there. And then obviously the result is we're testing how much max weight it actually holds. So think of it this way. This is really like an x value. The max weight is our y, or result, our outcome. I am going to stick with using the variables that they used in the problem. That'll just make it easier for you as we go along. So this first time, we're not talking about the distance of the board. We're not talking about the thickness. They are being held constant. So you don't have to worry about them coming into play. We're only analyzing W and M. So keep that in mind. All right. So if we look at our x values, which are really the W, the width in inches. So the width of our board is 1 inch, 2 inch, 3 inch, 4 inch, 5 inch, 6 inch. So you'll notice the list is ordered and it is going up. So we already know some characteristics about inverse and direct variation, that as x goes up, what should happen to y. So the very first thing you start looking at is x goes up, what is happening to y? 27 to 53, 53 to 80, 80 to 107, 107 to 133, and 133 to 160. That is definitely moving up. So in this case, we should know right now, as x goes up, y goes up. So we better be thinking it has to be one of our direct situations. You're saying, well, which one? Well, if we look at the two that we've been working on, y equals kx to the first, or y equals kx to the second, those are the only two we've really been focusing forward. And instead of the x and the y, you'll notice I went ahead and put the m for the mass, maximum weight, and W was our width of our board, so it fits. The independent variable is W. The dependent is the m, or max weight. So I've rewritten them, and so m equals kW, or possibly m equals kw squared. Those are our only two situations based on what we've learned so far in this chapter. Those are the only two direct variations equations that we've been studying. So now the problem is, well, let's look at the data and say, well, what relationships do we have? And you truly could choose any you wanted, but look at the x values to start with and ask yourself, do you see any doublings? Do you see any triplings? Something that would be small and easy. That's what we're looking for. So right now, there's several choices. If I took the number 1 and compared it to 2, that's a doubling. If I took the number 2 and compared it to 4, that's a doubling. If I took 3 and compared it to 6, that's a doubling. And you only have to choose one of those combinations. So if we don't want to make this too big, let's go with, we're going to double and make it the easiest combination you want. So some of you would just pick the 1 times 2 is a doubling. All right, so that's what's happening here. We're saying we're looking at data that is doubled. Now the question is, what happens to the m value? So when you looked at these, did our values come out with a doubling? Well, going from 1 to 2, 27 to 53, well, 27 times 2, because we know right now if we would use this equation, and it's a doubling, we would say m should get times by 2 times bigger. But if we chose the second equation, we're looking that m should end up being equal to 2 squared or 4 times bigger. So those two things, based on the fundamental theorem of variation we did the previous sections, we know those are the situations. So if you look, we went from 1 to 2 for the x, so we should be thinking, okay, 27 times 2 is about 54, so that's pretty close. 27 times 4, do the math. 7 times 4 is 28, carry the 2 is 108. So you're looking at two different m values. Which one is more characteristic? In this case, you're going to have to say 27 times 2 is much closer than 27 times 4 is. So with that situation, we're going to say that we have an m equals k times w situation for this variable. Knowing that, we should be able to go on to the next set of data, which will compare two different things. Again, this one was width and how it results to the final maximum weight. Okay, so with that, let's go to the next data table. And again, look at your original data table. You can see this time up on top, there's a statement that says distance d and width w are held constant. We're not talking about them at all. And actually, if you think about it, width, we just did in the last data piece, so we don't have to talk about it again. So we have the distance d and width, which are out of the picture, and we're talking this time about our thickness, which is really our x value, and our max weight again, which is what we're testing. How much weight will this board hold depending upon the different dimensions of it? So again, you can choose a doubling, tripling, quadrupling, whatever's easy for you. But that's what you want to look at. If we checked the doubling combinations I think are exactly as we had before. We could go 1 times 2, that's a doubling. We could go 2 is to 4, that's a doubling. And we've got 3 is to 6, that's a doubling. You're going to say, well, I don't want to use the same one every time. Well, if you like that, then maybe try something else. You could do a tripling. Look at the data. We could have a 1 times 3, which would represent a tripling. You could also do 2 times 3, which could represent a tripling. Now, luckily, we have nice whole numbers here. So you decide what you want, and before you even decide that, look at the values again. As t, which is your x value, went up, what happened to m, or the max weight? Again, it also went up. So you knew immediately that this variable t varies directly. And that's why you're seeing m equals kt and m equals kt squared as your only two choices. So from here, you decide, are you going to double? are you going to triple? It really doesn't matter. But then, here's what matters. If you say you want to double, and you're going to use this first equation, then you have to say, what result would m be? Well, m would have to be equal to 2 times our value, 2 to the first times bigger, because it was direct. But if we use it over here, 2, m would have to equal 2 squared, which is 4 times bigger. Go down to the 3 just to do something different. If m was our result, and we put a 3 in to this same equation, 3 would go in. It's to the first power, so it would become 3 times bigger. If we put the 3 into the second equation, our mass weight had better come, our mass weight had better become 3 squared, which we know is 9 times bigger. So double check that you are including your values there. Put a times sign, but I like the x a little better. So 2 squared, which is 4 times bigger. So let's look at your data. Don't do them both, pick one. I'm going to go with the doubling because I think, if it's there, that's the one you want to look at. All right, so go back to our data. Let's erase our combinations up there. Whoops, I erased my table a little, but it's not totally wiped out. Here we go. If I double, looking at here to here, I have to look at the max weight and see what happens. So I know this is my times by 2 for x. So this is showing, you can see 20 times what? And most of you will tell me it's a 20 times 4. So that means immediately that it is not this choice. A times by 4 was over here. So our variable of t, or thickness, varies directly as kt squared. And again, we have 2 out of the 3 dimensions of this board taken care of. We're ready to go to the third. This time, the only one left is our distance. A lot of people like to think of that as length of the board. So how long does this board have to be to support the max weight? Now again, take a look at our values. You can see them all now. We have distance being 1 foot, 2 foot, 3, 4, 5, 6. So as x went up, which is really the d values in this case, what's happening to the maximum weight? And most of you will say, oh, it's definitely going down. So if that's the case, we know now we are indirect or inverse. And what are our only 2 possibilities? Well, based on these equations, our 2 possibilities are the maximum weight can equal k over d, or a max weight can equal k over d squared. Those are the only 2 possibilities we've been studying. All right, so again, choose your doubling, tripling, quadrupling combination, and it can be anything, but let's just test our brain, make sure we're understanding. If we're talking about a doubling in this equation, then we know 2 to the first times smaller, because we're in inverse. If we're doing a 3, that would lead us to 3 to the first times smaller. And then again a 4, 4 times smaller. If it's a m equals k divided by d squared and we were doubling, then the result had better be 2 squared, which is really 4 times smaller. Versus if we did a tripling, that's what you're looking for, then it's 3 squared or 9 times smaller. Now you don't have to go through all of these every time, but whatever you see, the first number, that's the one I would take. Stick with the easy stuff. And so if we found 4 times bigger, then it would be 4 squared, which is 16 times smaller. So look at your data. You decide, you can look at your data, pick out what you like. Again, I'm going to go with doubling just because that is a small one. If it's there, I'd use it. So I know my d value is going from 1 to 2 as a doubling, but then I have to look, so that's my times by 2, but then I have to look and see what's happening. So I can definitely see that 800 divided by 2, or you could say 2 times smaller, And so a divide by 2 makes it 2 times smaller. So with that situation, we then know that 800 divided by 2 gives me my 400. It's only 2 times smaller. That would give us this inverse situation. So now if you think back, we have analyzed 3 different variables, one at a time. W for width, T for thickness, and D for distance or length of our board. They all go with the same situation. So the nice part about it is you should be able to write that one equation that shows the relationship of all the variables. So go ahead and write it down. Take a second. Put all the different relationships that you got together into one variation equation. That's the only major difference in this section. We were able to write them separately nicely. Now put them all together into one equation, and you now have your relationship for this situation. Okay, let's double check. Did you get that your maximum weight, which was the only y value we were testing the whole time, is actually equal to k, the constant, times w, which was directly, t squared, which was directly, and then our distance d was our only inverse. So even though there's more than one variable analyzed in the situation, we can write one and only one equation to satisfy the whole situation. We are going to discuss this new type of equation when we get into this last section, 2.9, this week. So take a look. We have 1, 2, 3 variables that are really independent, and we have the one variable m that is our dependent variable. And then, of course, we have our constant of the variation, which we'll always have. So that does it. Today you're going to be studying different tables of values from the reading, where you now have to first decide, is it a direct relationship or is it indirect? And then go with finding the variable. Is it times by 2, times bigger, times by 4, times bigger? You have to decide by looking at just the data. You do not have to do any number crunching. You do not have to find the constant of the variation. That's what's unique and different about these. So we will talk about more of this type of equation in the next section, but today we're done. So bring any questions you might have to class so that we can clear up any confusion.